Okay, so now we're on section 4.4, which is on L'Hopital's rule. Now, this here, L apostrophe H O with a circumflex, I believe, P-I-T-A-L apostrophe S, that is pronounced L'Hopital. It's a French dude. Now, apparently his name actually was spelled at the time Hospital, but a lot of people, when they see that, they start saying hospital. That sounds weird, so I really prefer to write it like this, L'Hopital. A lot of old French words that had an O followed by an S are more modernly written as O with the circumflex like that. So anyways, L'Hopital's rule. So L'Hopital's rule is going to help us deal with figuring out what's happening with functions sort of at the end. We've been talking about what happens in the middle of a function where it has maximums and minimums, where it's increasing, decreasing, where it's concave up, where it's concave down, etc. That's all talking about what's happening in sort of the middle of the graph. L'Hopital's rule is going to help us figure out what's going on at the end of the graph, specifically by letting us figure out what the limiting behavior of the function is to the left and to the right. Okay, so L'Hopital's rule is used when we're dealing with limits that are something called an indeterminate form. A lot of limits at infinity we can evaluate already, but there's some that we can't. In fact, quite a few. So an indeterminate form is a limit where just plugging in gives an undefined operation. So for example, if I take the limit of a ratio of functions, and if both functions go to 0, if I just plug in, I get 0 over 0. I call that the indeterminate form 0 over 0. Or if I have two functions which are going to plus or minus infinity at some limit, the limit f over g is of indeterminate form infinity over infinity. 0 over 0 is undefined, can't divide by 0. Infinity over infinity is undefined, that just doesn't make arithmetic sense. So we need something else to be able to deal with limits that look like this. Okay, so L'Hopital's rule allows us to deal with functions that are of the form, limits that are of the form 0 over 0 or infinity over infinity. And what it says is this: if I have a limit f over g as x goes to c that's of indeterminate form 0 over 0 or infinity over infinity, then to take the limit of f over g, I can actually take the limit of the derivatives of f and g. So the limit of f over g is the limit of f prime over g prime. And it basically says what we wish the quotient rule did say, so it's actually a little bit easier than some of our rules in the past. But this requires that we have 0 over 0 or infinity over infinity. So let's see an example. So let's take the limit as x goes to 1 of the natural log of x over x minus 1. We should always first check that we can apply L'Hopital. We can apply L'Hopital, which I'll be abbreviating as L apostrophe H, since as x goes to 1, log of x goes to 0, the log of 1 is 0, and x minus 1 also goes to 0, 1 minus 1 is 0. So in the past, we had some techniques for dealing with things that look like 0 over 0 or infinity over infinity, but we had to deal with, that only worked when we were dealing with like rational or algebraic type functions. This is not that, so we need L'Hopital. So the limit as x goes to 1 of log of x over x minus 1, we apply L'Hopital. When I do an equality that uses L'Hopital, I'll often write L apostrophe H above the equality to imply that that's what I'm applying there. So this is equal to the limit as x goes to 1 of the derivative of the natural log, which is 1 over x, over the derivative of x minus 1, which is 1. Then I check, can I plug in? Yes, I can plug in 1. I get 1 over 1 divided by 1, which is 1. So this limit is equal to 1. Now these indeterminate forms, they can actually, what is the value of the limit? What are the possible values of the limit? It turns out that the limits could be infinity, 0, or anything in between. So just because we have infinity or 0 over 0 doesn't mean that it's going to be 1. It can actually be anything. It depends upon how fast that thing on top and bottom is growing or how fast they're going to 0. So let's look at an example. Let's look at the limit as x goes to infinity of e to the x over x squared. This is of the form infinity over infinity because as x goes to infinity, e to the x shoots off to infinity, and x squared goes to infinity too. So this is L'Hopital worthy. We apply L'Hopital's rule, the derivative of e to the x is itself, the derivative of x squared is 2x. Then we check to see if we can plug in. Well, when I plug in, e to the x, as x goes to infinity, goes to infinity, and 2x also goes to infinity, because as x goes to infinity, 2x is twice that goes to infinity. So it's still infinity over infinity. That means that we can apply L'Hopital again. So sometimes we'll have to apply it more than once. Do it again. L'Hopital then gives us the limit as x goes to infinity of the derivative of e to the x, which is itself, over the derivative of 2x, which is 2. And now I have something that's going to infinity divided by a constant. So that means that this limit goes to infinity. So here, even though we have two things that are going to infinity, e to the x gets there first, it gets there faster, so the ratio of these two guys actually goes to infinity too. X squared gets to infinity, but much slower. Okay, now let's look at the limit as x goes to infinity of log of x over x to the 100, or x to the 1 over 100, so the 1/100th root of x. Now if you look at the graphs of these guys, they both look pretty flat, but log of x looks like it's going to be a lot bigger. This is a really small power of x. It gets to infinity eventually, but it gets there really slowly. So the question is, which is going to win here? Both of these things are going to infinity as x goes to infinity. So which is really bigger in the limit? Well, you apply L'Hopital's rule. L'Hopital's rule says the derivative of log is 1 over x. The derivative of x to the 1 over 100 is 1 over 100 times x to the 99, x to the negative 99 100ths. Okay, now this is going to be something where you can apply L'Hopital again. It is going to be 0 over 0. However, this is something that we can algebraically manipulate. If we can algebraically manipulate, we probably should. We should simplify this fraction first. So the bottom is the same as 1 over 100 times x to the 99 over 100. Then the ratio of two fractions is the top times the reciprocal of the bottom. So I get 100 x to the 99 over 100 divided by x. I can bring this power of x downstairs by subtracting 99 100ths from 1. That gives me the limit as x goes to infinity of 100 over x to the 1 over 100. And we've already talked about the fact that the reciprocal of any positive power of x goes to 0 as x goes to infinity. So constant over something going to infinity gives me something going to 0. Great, so this limit is 0. And now we've seen three examples where L'Hopital's rule can spit out a constant, infinity, or 0. Okay, so there are other sorts of indeterminate forms. For example, if we take a product of two functions, if one of the function goes to 0 and the other of the functions goes to infinity, we end up with 0 times infinity. This also is an indeterminate form. It could be 0, it could be infinity, it could be anything in between. So here we can't just say it's going to be 0 times infinity, it's 0, we need to work harder. So what we do here is we can't immediately apply L'Hopital's rule, but if we take one of these functions and put it into the denominator, then we end up with something where we have infinity over infinity or 0 over 0. So for example, if I take f and put its reciprocal in the denominator, then g still goes to infinity, but since 1 over f goes to 0, since f goes to 0, 1 over f goes to plus or minus infinity, we get plus or minus infinity. Or I could put the reciprocal of g into the bottom, and that will give me f over 1 over g. F still goes to 0, and since g goes to plus or minus infinity, 1 over g goes to 0. So as an example, let's take the limit as x goes to 0 from the right of x times log of x. X goes to 0, but log of x goes to minus infinity, so this is of the form 0 times infinity. Let's take one of these guys and put it in the denominator. Well, what's going to be easier to differentiate when I put in the denominator? X, the reciprocal of x, or the reciprocal of log of x? The reciprocal of x. 1 over log of x is going to be annoying to deal with. So let's take the x and put it into the denominator as x to the minus 1. Now I'm taking the limit as x goes to 0 from the right of log of x over x to the minus 1. Both of these go to plus or minus infinity as x goes to 0. This goes to negative infinity, this goes to positive infinity. Now I apply L'Hopital's rule. Take the derivative. Derivative of log of x is 1 over x. The derivative of x to the minus 1 is negative x to the minus 2. And now this is just algebra. I should do algebra here. I can multiply the top and bottom by x squared to get negative x squared over x, and then divide x squared by x to get the limit as x goes to 0 from the right of negative x. I can now just plug in x equal to 0, and I get 0. So x log x goes to 0 as x goes to 0 from the right. Let's look at one more example of an indeterminate product. Let's take the limit as x goes to infinity of x times arctangent of x minus pi over 2. Now as x goes to infinity, x is going to infinity. Arctangent goes to pi over 2, so arctangent minus pi over 2 goes to 0. This limit is of the form infinity times 0. So let's see what happens. Well, we need to take one of these guys and put its reciprocal into the denominator. I'm not going to put 1 over arctangent x minus pi over 2 into the denominator. That's going to be too crazy to take the derivative of. So I'm going to put x into the denominator instead. So the limit as x goes to infinity of arctangent of x minus pi over 2 over x to the minus 1. Now this is of the form 0 over 0. Great, so I can apply L'Hopital's rule. L'Hopital says take the derivative of the top, which is just 1 over 1 plus x squared. Pi over 2 is a constant, so it goes away. The derivative of x to the minus 1 is negative x to the minus 2. Then I do some algebra, multiply top and bottom by x squared to get negative x squared over 1 plus x squared. Now this is actually a limit that we could have handled earlier in the class. This is just a rational function, and we could do things like dividing the top and the bottom by x squared, and then see what happens. But we can also apply L'Hopital's rule here, so let's do that because this is infinity over infinity. So I apply L'Hopital. The top becomes negative 2x when I take the derivative. The bottom becomes 2x. Okay, those just cancel out, and I'm left with the limit as x goes to infinity of negative 1, which is just negative 1. So even though I have infinity times 0 here, this actually approaches the constant negative 1.